Our project states, for the following function, calculate using all needed procedures. What we need to calculate are the 10 steps of comprehensive graphing, which are: A. For the domain, we needed to look to the denominator. Since there is no restriction in there, since it's 1, the domain will be x belongs to all real numbers. To get the x-intercept, we equal the equation to 0 and solve for x, in which we get 3 values, which are the interceptions. To get the y-intercept, we plug the value of 0 to every x in the function and solve. To prove if our function is even, we set every x in the function as minus x. Since the function is not the same as the original when solved, it is not even. To prove if it is odd, we set the whole function times minus 1. The function that the result gave us is the symbol inverse version of our problem, so it is odd. For the vertical asymptote, we follow the rule that says polynomial functions of degree 1 or higher can have asymptotes nor gaps, because there is no restriction in the denominator since it is 1. So there is no vertical asymptote, and the same rule applies to the horizontal asymptote. To find the first derivative, we just use the power rule since it has no multiplication nor division in it. For the ID test, first we need to set the first derivative to 0 and solve for the critical points. So we factorize our function and we get 3 results. X equals 1, x equals minus 1, and f of x is undefined at 3. The local maximum and minimum are shown when selected a value that is less than the minor value of critical points and a value that is bigger than the one from the critical point, and a value that is in between the critical points. Then proceed to do the t-chart when we plot our values in the first derivative and observe how the direction of the graph changes. As it is visible from the chart, minus 2 and 2 have the same value in the sign, as a result that the equation where we plug the values is the equation of a parabola. The origin of it is a minus 3, which is another point or value given in the substitution. According to the results of our substitution, the local minimum will be minus 3 and the local maximum will be 9. For the second derivative, we did the same as with the first derivative, but using this one and the power rule. To do the concavity test, we use the same steps as in the ID test, but using the second derivative. So first we solve for x, then we plug the near values to x equals 0 in the number line, so we could get the concavity of the function. In the chart, it is visible how, as minus infinity approaches 0 in the graph, it has a negative concavity, and how as 0 approaches infinity, the concavity becomes positive. And to find the inflection points, we plug the value of x in the original equation. Finally, in the graph, we can see that the range of our original function is y belongs to all real numbers, and we can say that the relationship between the graphs of each one of the functions is that the graphs of the first derivative and the second derivative touches an important section of the original function. As a conclusion, we can say that it is important to do the ID test and the concavity test because you get to know how the graph of any function that is continuous is affected and its changes without actually graphing it. After the realization of this project, our results were:
created using Powtoon.